Done, yeah.
So thanks. So my name is Bosk. So I'm from KTH. I'm here to talk about some work in progress that I've been working on together with my now former TA, Selina. It's about introductory programming and variation theory. So I'll do a brief introduction and what we want to do with this work, and then I'll give a very quick theoretical background recap for everyone who isn't deeply familiar with variation theory and phenomenography. And then I'll get into some of the stuff we've been looking at, which is misconceptions and how you can use them together with variation theory to teach programming. So we'll look at some minor part of the results. And then I will also talk a bit about how this relates to the skill of debugging. So that's the plan. So let's start with a quick intro to what we want to do. So we teach lots of student programming. In our case, we use Python. And the students, they learn some, but not all usually. So misconceptions occur, and then usually we try to fix these misconceptions during tutoring when we discover them. And from a variation theoretic perspective, I mean, this when a misconception happens, that means that a student has discerned only some aspects of what is intended, but not all. So that's the key thing here. So we want to use the literature on misconceptions. There is quite some papers on that topic. To use those as phenomenographic observations and then apply this in variation theory to derive patterns of variation that we can use for teaching programming. So that's the overall view. And if you didn't follow exactly what that means, I'll dive into the details and give you a better description. So the questions that we are trying to answer here is, what misconceptions in introductory programming has been identified previously. And so that's what we are doing, so we don't have to collect data on our own, although we have done that a bit too. And then based on these misconceptions, analyze it through variation theory and see what aspects in terms of variation theory can we identify from the literature of misconceptions. And then what patterns of variation can we derive and use to allow the students to discern all aspects that they need to master this content to achieve the educational objective. And finally, how do these patterns of variation relate to the skill of debugging? We'll get back to that in the end. Now, let's go for a quick recap on phenomenography and variation theory, so you get the same kind of view that I have on it, so you'll better understand when we dive into the programming parts and those details later. So I like this quote from Ferenc Martin: understanding does not cause acts, instead acts express understanding. So that kind of summarizes quite well phenomenography, because you see acts from people and you try to see what they understand. So I mean, everyone is experiencing reality, and I mean, people interpret significant parts of reality. Some interpret some parts, others skip those parts. Depends on how you are as a person. So phenomenography is about recording this and try to understand how someone else sees reality. So as I said, acts is express understanding. So that's what we are after. And as an example of how we are going to apply this, so there is a nice example from Martin's 2014 book, Necessary Conditions of Learning. So there is this 6-year-old child, and the researcher asks, how many fingers do you have on your left hand? And the child replies 5. And then the researcher asks, how many fingers do you have on your right hand? And the child replies 10. Now, to a normal person, I mean, that doesn't make sense. I mean, you don't have 10 fingers on one hand and 5 on the others. So the question we should ask is, what does this 10 mean to this child? Actually, this was studied by Neumann a long time ago. And the thing with numbers is that they have 3 properties that are kind of crucial to understand numbers as normal people understand them once they've mastered it. And these 3 properties are the ordinal properties. I mean, you have first, second, third. You can order stuff. You have the cardinal property, so you can count how many there are. And you have the part-whole relationships, because you can add numbers together to get another number and so on. So this 60-year-old child that we just saw in the example had probably just discerned the ordinal property, but not the other 2 properties. And if you go to that view, so that you only understand ordinal properties, then having 10 on the other hand makes perfect sense, because it's the 10th finger you have at the end. And usually when you count the fingers, I mean, yeah, you name this one 5, and that's the whole collection, and then you name this one 10 when you reach to the end. So from that perspective, it makes total sense, those answers. And different children, they discern different properties or aspects at different times. And by using phenomenography like this, we can discover what these aspects are. And in our case, we will use the literature of misconceptions in programming. So because, I mean, this is exactly what happens when we teach the students programming. And sometimes they show us something and we see, okay, that doesn't make sense. You have misunderstood this. So by using these observations from all these misconception studies, we can actually do an analysis like this and build up what are the necessary aspects for different parts of introductory programming. So going over to variation theory then, so there is this nice quote also by Martin. So imagine that you live in an entirely green world and everything is green, and then comes a teacher from another world and he wants to teach you what the color green is. So no matter what he points to, it's green. So he points to something, oh, that's green, and he points to something else, that's green. It's impossible in this situation to actually learn what green is. At least I agree with that. I mean, on a philosophical level. And going to information theories, I totally agree. Since there is no difference, there is no information to be gained either. So several theories, I would say, argue for the lack of difference makes it impossible to learn anything. So the core of variation theory, I would say, is that, yeah, learning comes from discernment, which comes from variation, because if you don't have any variation, you can't discern differences. So that's the important part. And then the theory basically says that there must be a pattern of variation to experience to be able to learn something. And you must experience that variation to learn anything. Hence the title of this book was Necessary Conditions of Learning. So I mean, it's necessary to have this, but not sufficient, because other factors also matter. So let's have a look at one toy example before we dive into this. So there are 3 patterns of variation in this theory. So you have contrast, generalization, and fusion. And in necessary conditions of learning, there are only 3. He has removed that one. Yes. So
Right.
now I don't remember what was the name of the 4th one.
I have to look it up.
Yeah. Because I stumbled upon it the other day too.
Yeah.
That it was 4, but in necessary conditions of learning, he has removed one.
He has removed it.
Yes. So it's only 3 in that book.
Yeah, it's also cleaned up the difference between feature and aspect, which is good to know.
Yes, exactly. So looking at this play example, we have aspects and we have features. So an aspect contains several features. So for instance, in this particular example, where we want to teach something.
It's separation.
So, separation. Yeah, exactly. It was probably called something like that.
Yeah, it's called.
Mm-hmm.
I don't think I have to go and read about that.
Yeah.
Yeah.
But it makes perfect sense.
Okay.
This one, I don't miss that pattern actually. So
I use it a lot.
okay, we'll see how you read this book then. But anyway, so we have features and aspects. So in this case, we have the critical aspects. So the one we want to focus on is color. And the critical feature that we're interested in is blue, because this person we are teaching, they have never experienced blue before. So we want to teach that.
I think you're the first person I met who actually make this correct. Because people mix this up all together. So they call it color is the feature and blue is the aspect.
Yeah. No, you have to be really strict with that.
Yeah, that's good.
And then you have other aspects. So for instance, you have shapes, you have order, all in this image. So we see here that the contrast pattern, which is the first one here. So we have the green, which this person is familiar with since before. Maybe this is the person from the entirely green world. And then we just change. The only thing we change here is the color, because that's the critical aspect that we're interested in. So we should only introduce change in this aspect.
I choose to be the separation.
Okay.
Yeah.
Okay.
But I understand why it could be the contrast.
Yeah. So anyway, so then
you. I think
it's nice. Thanks. So we just want change in this particular aspect that we're interested in, and in this case, since we're interested in the feature blue, that is the color we change to. So that's the contrast. So you should change only in the aspect that you're interested in. The next pattern is generalization, and that pattern says you should change everything else except this particular thing that you're interested in. So that's why we change the shape here. So because to show that blue square things can also be blue. It's not just circles. And finally, the fusion pattern. That one is to bind everything together. So then we can bury everything, all the aspects together. So then we change the order, we can change color, we can change the other things. So basically you can see the contrast as finding this particular thing to focus on, and then the generalization for recognizing this thing in other examples, and then the fusion to see how this fits together with other stuff we've previously learned about. So the way to teach using variation theory is that you should have first contrast and then generalization and then fusion, and so you go between these. Now, funnily enough, I mean, when you look at general teaching where people don't teach according to this, I mean, there is a tendency to focus on generalization, and it's actually a nice read, this book. So it has some examples from maths in skolan, and you can see the problems that if you've ever taught maths to young kids, you can see some problems that arise from this. For instance, that a linear function is always y equals kx plus m. So it should always be y, it should always be x, can't be anything else, because all examples use that. So anyway, but the important part here is to use all these patterns. Now, the idea that we had was to look at all the misconception literature, try to detect what are the missing aspects in all these misconception examples, and try to find these aspects and then design patterns, so contrast, generalization, and fusion patterns to be able to teach this. So I'll tell you a bit about some of the results, because going through everything, that would basically be an entire introduction to programming course. So it would take far too long time to cover, but I'll focus a bit on functions and variables. Basically the areas we found, so I mean, we found misconceptions relating to, we tried to categorize them, and then we categorize them into functions and variables, conditionals, repetitions, types and classes. So basically all the major parts of our introductory programming course. So we found misconceptions in the literature basically everywhere. We also found some misconceptions among our students, because we tried to record misconceptions during, so whenever the TA was helping a student and they detected, hey, there's a misconception here, we noted it down to record it for later. And we found some that weren't already in the literature, but I won't talk that much about them. That's still further ahead to analyze. We haven't come that far. So we'll focus just on this, on a tiny part of the functions and variables part. So the one misconception that we came across was that the students believed that variables can hold an entire algorithm. So they seem to see a variable assignment as a function or mathematical equation. Most likely it comes from the mathematical equation. We'll get back to that. Another related misconception is that if a return statement contains an expression, then the student believes that the return value won't be just a value, but rather that expression. And it will update itself in the future if any values change. From a variation theoretic perspective, I would say two things about this. So first, variables and functions are rather interconnected, and we should treat them simultaneously to be able to contrast them to each other. Second, unlike maths, every line in a piece of program, in an imperative language that is, constitutes a new state of the program. So because the problem seemed to arise here, that they have their view from maths and how it works there, haven't seen the differences here. So we need to separate these. So if we would teach this, I mean, we would assume that the students know variables and functions and equations from maths, and that's like the only prerequisite knowledge. Then we can go in and try to teach them programming. So there are two critical aspects or dimensions of variation, as it's also called, because we will introduce variation in this aspect. So the first one is the type of object that an identifier refers to. And the features that we have here is function and data. And the data in turn, I mean, that will be divided into several types later on, but for all we care for here, it's either a function or it's a data. And by data, I mean, it's a value, the result of an expression. The other aspect that we find is what I call statefulness. And here you have the two features, stateful and stateless, because in maths, you don't have state, you don't have when you have a system of linear equations, for instance, you can just flip them around, the order doesn't matter, which it does in a program. So this is basically what Tobias Kuhn was talking about a few months ago, I think it was. So we had a brief discussion about this particular aspect then as well.
I have a question. So when you say type, you mean just the difference, there's functions and then there's data. It's the difference between those two.
Yes. So let's start with this idea of statefulness and how to introduce contrast for a student. So we have these two examples. So we start with the left one and execute this one, and the result is as expected x is equal 3. And that's what the students would expect. However, when we later add these two lines, now the students who show this misconception, they would expect the output to be x equals 5, but it isn't because we haven't updated x. So they see x equals a plus b as a function of some kind. But showing this, that this doesn't happen, then we introduce the contrast, so they see that, oh, we don't have as expected, so we need to. So now they know what to focus on, and then we can generalize this to other examples, so that they see that this applies in other places too, not just for the variable x, for instance, and it applies also in other with other completely different variable names and different settings, so we can generalize this. So the and then we can continue and eventually introduce here. Let's see there. Actually update the variable, and then we see that the output actually updates. And then we can go back to the previous example that we saw and show also that, okay, if we add the c equals here, we actually get the updated version. Now, so this was the statefulness. So we didn't do any fusion because we only have one aspect that we're interested in. So fusion will come later. Now the next aspect that we have, the type of object that an identifier refers to. So we need to be able to separate functions from data. So basically, the misconception and the aspect that the aspects that they have discerned comes from maths, and where you usually write y equals kx plus m, and there it's implied that y is a function, and you can just rewrite it to get any function, whereas actually y should be a function y of x. But due to that implicit parts in maths, I don't think they have discerned how it actually is. So in some sense, I mean, this has made me think of high school maths as kind of, so usually people say that, okay, Python has dynamic typing, and that's kind of bad because you get lots of bugs. But I would say that high school maths is kind of like the Python of maths. It's dynamically typed, and it's not until you get to university you get strict typing in maths as well, because I mean, a function is a function in maths as well. You can't just change it to anything else. So they kind of go hand in hand there. But to introduce this to the students, we have to contrast functions and data. So we have this example from before, where we updated a and b, and we didn't get an updated x. So we need to contrast this with the functional aspect where it actually would work, which would be to rewrite x as a function of a and b, and then show that, okay, so now it actually is a function, so now it works. And then generalize it to other cases as well, that, okay, if we do this, we actually get the functional behavior that we are expecting. that we didn't get before. And then we can get to the fusion to fuse the functionality of functions with the statefulness. So we can change the order and see that the statefulness that we had still applies here, although it doesn't apply in that. And we can do this with several different examples. Now there are some other aspects also of functions that we should cover. So in this case, we are interested in another misconception that is quite common. That is the names of the variables and if they matter and the order of how you pass them in, because it's common that in this case the students usually they have the name, so it's the same variable names here and here, and then they think that the order here doesn't matter, it's the names that matter. So that's a matter of so the aspect that's interesting is scope for that particular misconception. So we can introduce the contrast here by switching the order and seeing that the order in the output actually switched as well. And then we can return to all the previous examples where actually the order was correct to show that, hey, if we look at the order of all the other examples, we can generalize this to other settings as well. Another problem that we have is the naming. So I mean, previously we saw the order of the variable names, and that those matter. And another part of that is the scope, so the actual names. So in this case, we don't vary the order, but we do introduce variation in the naming of the variables. So we change the names here, so they are not the same as they were up here. So that introduces contrast. And we can generalize this even further by just removing the variable names entirely, so that they are unnamed and just values that we pass in. Now, so this kind of illustrates the types of patterns that we have started working on deriving. So we're far from done, but we've done most work on functions and variables here. So this was a small taste of that. But the realization I had when doing this, when dealing with variation theory and looking at all these misconceptions and these things, was that I started thinking about how I do debugging, because it occurred to me that I have some interesting variations, because basically when I do debugging, I introduce variations. Which is interesting, and it relates to one part in necessary conditions of learning. When I read that, because Martin does a nice analysis of scientific discovery and relating that to these patterns of variation. So basically, he analyzed Copernicus and his discovery of centricity, as he called it. So the contribution was not the heliocentric view, but rather the discovery of centricity, that things can center on different things. Because he opened the dimension of centricity, so where you have the heliocentric is one feature and geocentric is another feature. So he introduced that one, and he did go into the details of how these discoveries were made. So he has also an analysis from Darwin. So the nice thing with Darwin and Wallace, who independently made the same discovery that led to the theory of evolution, they are documented in their journals, and they were independent. So he sees the observations that they did in those journals, and saw that, hey, here is the contrasting part. And then they went on to do the science, which is the generalization. So it's kind of a beautiful view on the whole thing. But it made me think how this relates to debugging, because basically a bug is just an unknown that we need to discover. Yeah, I observed the types of variations that I introduce in my code when I try to do debugging. So my hypothesis was that, okay, probably these patterns of variations are related to how well you're doing at debugging. So if you're good at debugging, you're good at introducing these patterns of variation for yourself. Martin also had a section in the book where he returned to surface and deep learning many years ago, and he concluded that deep learning, where you actually learn to understand, students who have a deep approach to learning, they actually introduce these patterns of variation for themselves when they are studying. So these things make me think that this should be kind of related to debugging as well. So now I wanted to do a small test on you. So I suppose all of you know programming.
Absolutely.
Yeah.
I vouch for every single person in this room.
Yes. And hopefully you're familiar enough with Python. So we'll start with a contrasting example. So you have these two code snippets. So if we first look at the left one, so we have this function expand, which takes a list and just expands it with one element 1 and returns the result. So we see that if we, and it uses a default parameter, so that if we pass in the list containing just one element 1, then we get back the list containing 1, 1. And if we pass in the list containing just the element 2, we get 2, and then we have appended 1. And if we use the default value, which is an empty list, yeah, we just add 1. So these are expected. But then we change our code in the following way. So we just add this element directly to x, and then we return x. So instead of x plus 1, we just modify x and return it. And we see here that if we do that for the first two, yeah, it's exactly the same behavior. And for the first one here, it's exactly the same behavior. But when we do this call, so we see it's the same two calls here, same as we did before. We don't pass anything, but the return value changes. How would you approach this, debugging this behavior?
Obviously some problem with the program. I'd probably run it again.
First compile, so run several times.
Yeah, exactly.
That will solve it.
So actually, I'll see. I'll show you how it is when you run it several times.
I'll just run it until it works.
Yeah. So let's see. I'll switch the screen share. Okay. So here's the exact same program. A bit more commentary.
Sorry, can you make the font a bit bigger, please?
That'd be
possible.
Control plus. Do you have that in Emacs?
Max. That was an insult.
What is it then?
This is Vim.
Oh, you have it split.
Yeah. Huh?
Oh, that's nice.
Yeah, so let's see, I should have, why didn't it change the font size?
So Vim is but that's a newer version
that
of
works.
VI, I think.
Yeah, exactly.
So you don't use VI?
No. So Vim has the extensibility.
I have a colleague who uses VI.
So, but we can.
Yeah, all of them, yeah.
So this is exactly what happened, the output from before, and if we call let's see, we need to experiment.expand. So if we continue on this one, yeah, same thing happens there over and over. Okay, as expected. And then we make our change. So there are two ways to make the change. We either just
well, don't tell me you can do plus equal and have it. No way.
now we can do either that or
Oh yeah, do that, that's better.
or the x dot append or
What's it?
x dot expand. Either works. So all of those here, it's the same version, same thing to do, different. So experiment. Okay, and now we see that the last one here changed. So if we run this one, the more we run it, the more it expands. That's super weird. So think of it. How would you approach this debugging it? I'll drink a bit. What do you think?
There's nothing wrong with it. It's just that you just treat it in different ways, you know. In one way, you actually change this variable. In the
How
other
do you
one.
define what's right?
Yeah.
Yeah. So most people. So okay, if you just do a quick googling, most people on the internet would say that this is totally wrong. But then they have probably experienced other languages where this is not true.
Work like this.
Yeah.
It's a bit weird.
Yeah. So was there anyone who expected this to happen, or because most people don't expect this to happen?
I've only heard legends of things like this happening, and I never thought I would see it for myself.
Yeah. So, but do you have any idea of how you would try to debug it if this could happen in your code?
Well, I feel like it has something to do with this 10-year-old who has 10 fingers, or this 6-year-old who has 10 fingers on one hand.
Of sorts.
Well, you can use the debugger and look in the memory and see.
I would try debugging it with different values, honestly. I was like, oh, is that something like I would probably first try to see if it works with 2, 3, 4, 5, and 6.
What do you mean? So
You know, instead of adding just one, oh, is it something weird about when you add just one? Okay, let's try to add 2, and then
you mean like changing it?
yeah, changing the value, and then it would work. I imagine it works the same way.
Okay, let's reload it and see what happens. Oh no, it didn't reload. I need to exit this one.
No, I wasn't it.
Next step, what would you do?
I would probably. Well, what I'm curious about is if you take away the equals, the empty array in the after they expand.
So
No, not that one. In the function call or the function declaration. If you take away the equals, the empty array.
So you don't want the default value.
Yes.
Well, if you don't have the default value, you won't. Then you have to pass something in, and we saw that if you pass something in, it works as correctly as intended. Then it's nothing weird.
Well, what happened? Well, if you run it now, or does it now it's a different behavior, right?
Yeah, now you won't be able to run the.
Or is it an error?
No, well, it would be an error to call it without any argument. So if we import it now, it fails on these functions.
But now if you call it with the empty list.
So I pass in the empty list here.
Yeah. I mean, this is just how I would debug this. See,
But
I think that,
I wouldn't debug it, I would try to understand what's, I mean, in one case, it points to, it says the reference back.
but
And the other way.
yeah, but now we fixed it.
Just change the.
Yeah, now it works. It worked before too. As long as you pass something in, it works. It's if you use the default value,
and
it's weird.
I think this is so indicative of like introductory programming. When students are trying to do something like this, they get some error exactly like this, and then they just do it some other way, and they totally jump over it without actually understanding the variation or understanding how the behavior. They're just like, oh, I fixed it. Don't have to understand. Don't have to understand the importance of having these default parameters.
So so the way I would teach this to see, I can probably stay in the terminal actually. Oh, we can switch back to the slides first and then we return to the terminal. So I mean that was the contrast to introduce okay what to focus on. It's when we use this default value, it's weird. When we don't use the default value, it's fine. So then we need to generalize this using the generalization pattern, which means that we vary the non-critical aspects, which means we can vary everything else but keep this behavior. And that's what we want to do. And so we want to keep this critical aspect invariant. So this is also what is known as the scientific method. So the hypothesis testing, and you try to generalize something. So let's dive into some other examples. So because I designed, I thought of some patterns how to teach this and explain what this is. So the second pattern, second thing I would do would be this case. So now we have this function here, which is full of these default values. So it has a default value for first name, a default value for last name, and then a person base, which has a default value of a person object in this case. And this create person function simply creates the person and fills in first or last name and then returns the person object building. So if we run this one, we see what happens. So it the first thing it creates the default person, which is Gina Jones, as we saw. So the first line of output is expected here, and then we create a person and we change the first name to Ada. So the output is Ada Jones. That's expected. Makes sense. And then we create another person and just change the first name to Beda, and we get Beda Jones. And then we just print these different objects that we got. So I mean, we created here we created the person default, and we created person A, person B, and judging by the output up here, they got different names. But when we later, in the end, print person B, person A, person default, then we see that all of them print the same thing. So obviously, that's not what we intended. So it's related to Python's passing. What did you say, B?
Features.
Features, yeah. Passing objects by reference. So we receive the same object and we're modifying the same object all the time. So that's one step in the right direction. So what would be the so we still maintain the property here. So let's see what does the next experiment what would that one be? So the next experiment that I would do would be to create this class, which I call the trace class because I want to see when our objects created. So the only thing this object does when you instantiate this class is it prints this object was created. And then we have this test function, which has a default value of this trace object. And then the function call, and then we run the main program. So the key here is that the first part of the test program here is print test code begins. So normally that's the first thing that should be in the output. So if we run this, we see that that's the second thing that pops up, not the first thing. So we see here that the default object, the default parameter for this function was created before execution of the program began. Which means that when the function is defined, that's when Python actually creates all the default values, and then it keeps them. And otherwise the code executes as expected. So if we go to another experiment where we just have another function. So now we're entering Fusion here to fuse back with the other properties and the other types where this property doesn't exist. So if we run this one, we see that the output here, we have the same x plus 1 here, so we modify x just as we did with the list, but here it's 2, 2, 2 instead of increasing it. So what happens is that it's the reference, because a list is an object, and all objects are passed by reference in Python, so it keeps them. And that's not true for integers. So they are not modified and not used by reference. So there we have a copy. So that's why it happens when we have a list or an object or something, but not here. So these were the patterns that I derived to actually teach this according to variation theory. And then, yeah, we fused it. And then,
Sorry, just a question about this.
yes.
So when you come here all of a sudden, I mean, you have this default assignment, so the X is set to 1 at the beginning of the program.
Mm-hmm.
But then it changes. You're getting new.
Yeah, you get a copy every time.
Yeah, you get a copy
because it's not by reference.
Yeah. That's so intricate. It's
Exactly.
so complex. I don't know. I mean, I think this is really. I mean, this is stuff that I think we send students out of the bachelor's program, and they.
We tried to teach it in CS1. I failed.
Exactly. No, but it's yeah. So that's the thing. So I mean, it happens in some cases, but not in other cases. Now, so the key here is that so the way I would debug it myself is also the way I would teach it according to variation theory. So I tested it on a colleague, exactly this test, and well, he had to work until he solved it and finished it. It took him an hour. I had estimated, okay, it will take at most half an hour. But yeah, it took an hour. He was a bit frustrated at the end, but yeah. The observation I made then was that, yeah, he also had to run through these patterns. I mean, the values he used weren't exactly the same as I did. I mean, he didn't name the class the same thing and those things. But the patterns appeared there. So I want to test this with several colleagues and see how they would go about and do the debugging pattern. And I would like to look into the data set of all your students when they encounter errors and see what patterns they do, what changes they make to try to solve it.
Heck yeah.
Because those who do it fast, to solve the problem fast, they are probably very good at introducing this variation and getting to the right place.
Or they are just lucky, or they skip it.
Or they ask the teacher.
As according from the lens of data analysis, that's the same thing. They're they're smart.
We just ask Palle who
Yeah.
gave their answer, his answer, and they never understood.
Yeah,
it.
but we have Pallet's code too, so that'll be fine. It's just a cross-reference.
Exactly. So, but it would be interesting to see how the students do, and particularly those who struggle a lot and really can't debug their programs, how they do, and those that find programming to be easy and they solve their bugs quite quickly, how they are doing. Compare them from this. So Martin had another interesting observation in the book about generative learning, because there was a series of studies where they observed the delayed learning effects. So because they had taught according to theory, and then they saw that the students improved a while later, not directly afterwards, but benefits came much later, and they cross tested so that they were sure that, okay, it wasn't that they were taught this later, but it was actually because they had students trade class and so on, and then go back to their normal class to compensate for this. So they suspect that that's due to some generative learning, and they couldn't see such effect with those instructed without the patterns. So my idea is, okay, if I teach the students with these patterns, if I teach them programming using these patterns, there might actually be a generative learning effect, meaning they get better at debugging this type of thing that I teach them. So once I taught them in the entire course, they might improve in debugging, in their debugging skills for these things. So that's something I would also like to investigate further. And that was what I wanted to say. So open for discussion.
So should we stop the recording?